Alright, in this video we are going to introduce the complex plane in a very simple way to talk about how to graph them as well as find their modulus. Complex numbers, remember, and I'm going to draw a quick diagram of the number system. You're welcome to watch this awesome video that will kind of give you an introduction to complex numbers and maybe a little bit of a cool graphical representation in 3 dimensions if you'd like to watch that. Otherwise, let's just remind ourselves a little bit about the development of the number system. So it started with the natural numbers, right? These are numbers like 1, 2, 3, numbers I can count on my hands, but go for an infinite in the positive direction. Later on was added the 0, which now constitutes the whole numbers. After that, we then added the integers, so we added negatives to our number line. And eventually, we also added fractional values, and we call those fractional values rational numbers. And rational numbers then kind of branched us out to irrational. We introduced radicals, and we had things like square root of 3. These were our irrational numbers. Rational and irrational numbers make up what we call the real number system. All of these numbers can be represented on what we call the real number line, right? If I were to draw a number line, 0 sits here, and everything positive goes to the right of 0, everything left moves to the left of 0, everything negative moves to the left of 0. And pretty easy to understand as far as directional, and every value found within this box can be placed on the real number line somewhere. Okay. Now, outside of the real numbers, we have what we call imaginary numbers. Imaginary numbers are any numbers that have a negative square root value, so square root of -1, and we represent them with an I, as you can recall in that section that you did. And and this is kind of the last big set that we looked at, but when we put these two sets together, we create what we call complex numbers. And complex numbers, they have both a real piece, so like the number 4 is a real number, plus an imaginary piece, so let's say 3i. 4 plus 3i represents a complex number. So what is this little complex number and why is it helpful? So let's just jump down here. Sometimes it feels like we're introducing a new language when we do complex numbers, but you'll notice that the complex plane looks very similar to the coordinate plane because left and right, up and down just makes sense when we're drawing on a planar surface. So notice here's the real number line, kind of like I drew up here. This is the real number line. When we add an imaginary number line as like the y-axis, then we add this further dimension of numbers. So let's just talk about how to graph one of these. A complex number over here defined, z, is given by a pair of real numbers, x and y, and is written in the form z is equal to x plus y. Notice there's our real number piece. There's our imaginary number piece. Now we always put them in this order. This is called standard form. And the x and the y actually represent a point on the graph. The x moves us in the real number direction because it is the real number piece, and the y moves us in the imaginary number direction, up or down. So if we wanted to come down here and plot, say, a number called w sub 1, complex numbers are often written with z and w, and then we use subscripts to denote different complex numbers. So let's say we want to graph this right here. W sub 1 is equal to 4 plus 2i. Again, 4 plus 2i means 4 units in the real direction. And because it's positive, we're going to go to the right. Then we will go 2 units in the imaginary axis direction. And because it's positive, we're going to go up. So this is going to move, and I'm going to draw some little tick marks really quick. Let's put some on there as evenly spaced as possible. So 4 to the right, up 2, so 1, 2, 3, there's 4, and we're going to go up 2, and I'm going to place that dot right there. That represents W sub 1. Okay, we could do the same thing with W sub 2. We could plot this on here, so W sub 2 is -5 plus I, so that means -5 is left 5 on the real axes. So -1, 2, 3, 4, 5, and we're going to go +1, right? Because that's like a +1 coefficient in the imaginary axis direction. So that right there would represent W2. Then the last one, W3, if I was plotting this one, let's grab a different color. W3 is equal to negative 2i. So notice there is no real part on this one. We're not moving left or right at all. We're just going down 2 in the imaginary axes, and this would represent W3. Plotting on the complex plane, not too complicated. Again, we just write them in standard form so that we can treat them like a coordinate point on the plane. Now, remember when we dealt with conjugate values, we represent the conjugate of a complex number. So if the complex number z is defined as x plus yi, its conjugate, or in other words z bar, with this bar over it, is equal to x minus yi. So this z bar is kind of the new part. We've talked about the conjugate already. Hopefully you did that in a previous section. So z bar represents conjugate. So down here it says write, plot, and label each of the following on that same coordinate axis above. So this first one that we have, I'm going to go back to blue because it relates to that one, is the conjugate of W1. So if W1 was right up here with 4 plus 2i, its conjugate would be 4 minus 2i. We just negate or change the sign of the imaginary piece. So if I want to graph that, again, it's going to go 4 in the real direction, and then this time it'll go down 2. So W1's conjugate, we put a bar above the top, would be represented there. W2, so I'm going to go back to this coral color. The conjugate, again, is this one up here. So if I negate the imaginary part or change the sign of that imaginary piece, then I've got negative 5 minus 1i. No, I don't need to write the 1. I'll just write it there to help us remember. We're going to go left 5, so left on the real axes, and then down 1 this time for its conjugate. So that would be W2, bar on top to show that it's the conjugate. And then if we do that last one with W3, again, it was at negative 2i, so that's the same thing for its conjugate, would be a positive 2i. So this one is going to go up 2 on the axes, not moving left or right in either direction. So here we have the conjugate of W3. Okay. Notice those conjugates are just reflected over the x-axis because we are just negating the imaginary portion on that. This notation also allows us to represent complex operations. So remember when we add and subtract complex numbers, we just combine like pieces. So if we look, say, at number 1, we have W3 plus W2. Well, if we come back up here to our complex numbers where they're defined, W3 is right here, so I'm going to write these out. That would be like saying W3, right, plus W2, and W2 is up there, negative 5 plus I. So I'm going to write this in parentheses just so you can see. There's negative 5 plus I, and here was W3. So we're just adding these complex numbers. Now remember, when you add them, you just add like terms. So this imaginary piece will combine with this imaginary piece. So I have negative 2 plus 1. And the negative 5 stays out front as the real number piece. It doesn't have anything to combine with. Negative 2i plus I would be negative 1i, or in other words, just negative I. Okay. Over on the right, we have number 2. It says W1. So we have 4 plus 2i taken from up here, W1, and then we have plus its conjugate, so plus 4 minus 2i. So when we add these conjugates here, 4 plus 4, those real number parts, gives us 8, and 2 minus 2i would be 0, so this one just gives us 8. W2 minus the conjugate of 1, so again, if we take W2, we've got negative 5 plus I. We subtract the conjugate of W1. So again, you can find that above if you've forgotten. It's 4 minus 2i. And this one's subtraction, so just remember, make sure you apply that negative as you subtract. So we've got negative 5 minus 4, be negative 9 for our real number piece. And we've got I minus a negative 2i, which is really I plus 2I, so this would be plus 3I. And then lastly here, we've got number 4, which is 2 times W3. So 2 times W3 is going to be equal to 4I in this case. Okay. Moving forward, if we think of complex numbers as representing a vector on the plane, we can also relate these complex number operations as directional vector operations. So let's just kind of see if we can represent some of these. Now, a couple of these are going to jump right off the graph, so I'm going to try and stick with the 2 that will, I believe, stay on the graph. So let's try a couple of these. Now, we're given 4 graphs here. 1, 2, 3, and 4. I'm going to look at number 1, and we're going to see if we can represent number 1 with vectors on this plane. So I don't know if you guys remember doing vectors, but remember vectors have the 2 components, and we write them either as a matrix or we use these little, they almost look like angle bars. But really this is like the horizontal component, and this is the vertical component, so it works a lot like a coordinate pair, x, y. And we're moving from x to y. And we can use complex numbers to kind of represent that. We always move in the real direction first, and then in the vertical direction. So if I wanted to start with, let's say we start right here with W3. So I'm going to start with W3 here, and I'm going to write it as a vector so I can graph this, but really it works the same as like the complex plane. So looking back up at the very beginning, W3 was equal to negative 2I. So really we moved 0 in this direction and down to here. So I'm just going to graph that. 0 down to this right here represents that vector. Now, if I go from that vector and I want to add, now this is terrible notation, but I want you to kind of understand what we're talking about here. If I want to add W2, this is all coming from right here, number 1. W2 is equal to, right, the vector. If we look up here once again, the one in red, negative 5 plus I. So negative 5 and 1 in the vertical direction. So if we go negative 5 and up 1, that puts us clear over here. But remember when you did vector addition and you wanted to add the next vector, you started at the end of where the last vector left you off. So you're going to go left 5 and up 1 from the point where you left off. So this guy right here represents that vector addition, right? This one went down, we then added this vector, and the resultant vector is the one from the origin to where you finish. So if I draw in this final vector, let's go back to black, we're looking at this one right here that would represent W3 plus W2. So if we look at that, notice that one is to the left 5 and down 1. So if I was writing W3 plus W2 based off this graph, I would say, well, it finished right there at the point negative 5 and down 1. And if you look at up at what we got when we added those complex numbers, just using complex operations by combining like terms, you will get the same thing. So the graph, it just kind of shows us that representation of where it's moving about the graph when we're adding those vectors. Let's just look at one more, maybe graph number 4. Again, this one is 2 times W sub 3. So if we look up here, again, W3, the original one in the green there, was negative 2I. So if I come down here, and again, that's kind of where we started the last one. Oh, I'll use a different color so you can see it better. It's down at negative 2I. When we look at that, we can also then represent that being multiplied by 2, as it says in number 4, so 2W to the third. We just put another one on there, right? So this multiplied by 2 means it goes down to from there. Now that means our stopping point is right there at negative 4. So if you notice, 2W to the third, if we were writing the vector from here to this stopping point, that would be over left and right, right? 0 and down 4. So when we look up at, oh, did I go the wrong direction? Negative 2i. Oh, I did number 4 wrong. I just forgot my negative. So notice that's a negative 2i. I used the conjugate. My mistake. So negative 4i. That was a good way to check. So again, we can notice that complex number multiplication can really be represented or related to those vectors. This will be the finished or the end of this video. We will then talk about the modulus of a complex number in the next video.